as you go across a row. And you would say atomic radii decreases because of nuclear charge, because the nucleus is pulling those electrons in even more tightly because it doesn't want to let them go. Okay? Now, on your slides, I think, guys, this is slide number 9, and we just talked about this. Energy levels and shielding have an effect on the group. And nuclear charge only has an effect on a period or on a row. So we already talked about that. Now, okay, slide number 10. So on slide number 10, there's something that's called an isoelectronic ion. Iso meaning equal, and electronic meaning like numbers of electrons. So equal amount of electrons. That's what this is meaning. So I gave you a group of isoelectronic ions. That group would be the Al plus 3, Mg plus 2, Na plus 1, Ne, F minus 1, F minus 2, N minus 3. I'm sorry, F minus 1, O minus 2, N minus 3. I want us to write the electron configurations for each of those because I want you to understand why they would have the same amount of electrons. So we know, let's start off with the first one, aluminum. We know that aluminum, neutral aluminum, has 13 protons, and if it's neutral, it would have 13 electrons. So 13 protons, 13 electrons. But it has a plus 3 charge, which means that it gave up 3 electrons, right? Because that means it has 3 more protons than it does electrons. So if it gave up 3 electrons, it really doesn't have 13 electrons. It really has 10 electrons. So 13 protons, 10 electrons. Let's look at magnesium with a plus 2 charge. Magnesium has 12 protons. Right, so magnesium, I just look at the atomic number, it's 12 protons. And if magnesium in this case has a plus 2 charge, if it was neutral, it'd have 12. But in this case, something happened to the amount of electrons I have. And since it's a plus 2 charge, that means I have 2 more protons than I do electrons, which means that magnesium must have given away 2 of its electrons. So since it gave away 2 of its electrons, it will have 10 electrons. Okay, so aluminum has 10 electrons, magnesium has 10 electrons. Now we also had sodium. Sodium was a plus 1 charge. I know it has 11 protons. Since it has a plus 1 charge, that means it gave away an electron because it has 1 more proton than an electron. So that means it also has 10 electrons. All of these have 10 electrons. Let's think about their electron configuration as well. Originally, let's just write sodium, because sodium may be a little easier. So I would have written sodium's electron configuration as 1s2, 2s2, 2p6, 3s1. So this would be sodium's electron configuration, 1s2, 2s2, 2p6, 3s1. If sodium gives away an electron, it's going to give away that electron on the outermost shell. Which one of these is sodium's outermost shell? The 3s1 is. That's what we said, remember, its valence electron was. So it gives this away. Sodium's electron configuration would actually look like 1s2, 2s2, 2p6. So it actually looks like this. What element has this electron configuration? 1s2, 2s2, 2p6. You should be saying neon. Neon has this configuration because when sodium gave that up, this one little extra electron away, it became stable. Think about Bohr's model. Its outer shell would then be full. So isoelectronic ions mean that they have the same number or equal number of electrons. So they're all going to have this noble gas configuration. If you were to do the exact same thing that we did here with sodium, with aluminum, magnesium, fluorine, oxygen, and nitrogen, you would find that all of them have the same electron configuration and they all look like neon. Now, and I have that written down there as well. If you go to the next slide, though, their atomic radii will look differently. They may all have the same electron configuration when you have compared the charged with neon, but their sizes are different, and there's a reason for that. As we look at this slide number 11, I see that positive ions have more protons and less electrons. So because of that, that means that nuclear charge is going to come into play. So that means the nucleus is going to pull on those electrons and hold them so tightly that they don't want to let those other electrons that they have go. So aluminum that has this +3 charge is going to be the smallest. It has more protons than it does electrons, so it's the smallest. The next one that has the most protons would be magnesium, because it has 2 extra protons than electrons, so it's the next smallest. Sodium would be the next, because it only has one more proton than electron. You see neon, and then you can see all of the negative charges. The more negative charge that you have, the bigger that atom or atomic radii will be. And I want you to think about why. As you have more electrons, you have a greater opportunity to shield, or you have a greater opportunity not only to shield an electron, but it just becomes so much bulkier. The nucleus can't possibly pull on that many electrons all at the same time. So I want you to remember that positive ions, the more positive an ion is, the smaller the atomic radii it will be. And the more negative that an ion is, so like nitrogen, which has a -3 charge, the larger the atomic radii it will be. So guys, if you look at the next slide, number 12, it says, which element has the largest or larger atomic radius? The first one I asked you to compare Na or Cs, so you're comparing sodium and you're comparing cesium. The first thing, if I ask you to do a comparison between the two, figure out if they're in the same group or if they're in the same row. That's going to be what helps you first. So if I look at sodium and cesium on my periodic table, I know they're in the same family or column, okay? I know my trend for atomic radii is that atomic radii increases as you go down a column. So which one would be bigger? Would it be sodium or would it be cesium? And you should be saying cesium because it's further down the column, has more energy levels, more shielding. So cesium would be your larger one in that case. Okay guys, the next one was sodium, Na, or Cl, which was chlorine. So if you look at those two, are they in the same column or are they in the same row? And you should be saying they're in the same row. They're both in the third energy level. So as I know my trend for atomic radii would be that as I go across the periodic table, I know that atomic radii decreases. So sodium is the first one in that row. Chlorine is really close by a noble gas. So I know that sodium must be the larger one because chlorine is going to hold or hug those electrons really close. Nucleus pulls them in very tightly. So in that case, I would say that sodium would be the larger one. Okay, next I have potassium or I have K+. I have potassium or I have K+. Now, we could draw this to also help us kind of understand why one would be larger than the other. Now, I told you kind of this general trend that positive ions are smaller. Positive ions are smaller. If I had just drawn potassium, so if I have potassium, I know that potassium is in the 4th row. So I'm going to have 4 rings around it. So I have K, 1, 2, 3, 4. And I have just one. I have just one on its outer shell. So all of them are full except for the one on the outer shell. That's what potassium would look like. If I drew K+, that means I gave away an electron. So if I gave away that electron, what happens to that outermost ring? Well, it goes away. So that means instead of having 4 rings, I would only have 3 rings. So my Bohr's model would actually look like this. So potassium with a +1 is smaller than potassium that doesn't have a charge. So that's why this one's smaller, because when this one lost an electron, it lost that outermost ring. So it lost a whole energy level, which that's what makes an atom a lot bigger. So K+1 would be smaller, but in this case they asked you which one is larger. So you would say that potassium without the charge, the neutral potassium, is the larger one. All right, guys, I gave you one more problem that I wanted you to do. We had O, or we had O with a -2. Now, in this case, it's kind of like that opposite. So I know that a negatively charged ion, or a negatively charged element, actually is bigger. So if you remember it that way, then I would say that O with a -2 charge has a bigger atomic radius. All right, let's move on, guys, to your next trend, which is ionization energy. Now, ionization energy is just the amount of energy that you need to get an electron or to remove an electron from that outermost shell. If you think about noble gases, it is going to take a ton of energy to pull an electron away from those noble gases. Now, I wrote on here that there is a first ionization energy, there's a second ionization energy, there's a third ionization energy, so on and so forth. All that means is the first ionization energy means the amount of energy you need to pull one electron, or the first electron, from the outermost ring. Second ionization energy means the amount of energy you need to take the second electron away from that outermost ring. The third ionization energy means the amount of energy you need to take the third electron away from that outermost ring. We're only going to focus really on the first ionization energy. So as long as you know that ionization energy means removing an electron, or the amount of energy you need to remove an electron, we're good to go. Now, the group trend for ionization energy would be that as you go down a group, which means column or family, as you go down a group, the ionization energy will decrease. I want you to understand why. You're adding more and more energy levels, and there's more and more shielding that's happening between these electrons. Because you're adding more energy levels, the attraction of that outermost electron with the nucleus. So here's my nucleus. If I am all the way out here, the attraction between the nucleus and this electron is pretty weak. So as I continue to add more energy levels, the attraction becomes weaker and weaker. It doesn't take a lot of energy to pull an electron off of this outermost ring if it already has such a weak attraction. So that's why as you go down a column, that ionization energy decreases, because the attraction between the nucleus and the electron is also decreasing, or becoming weaker. Now, when we think about ionization in terms of a period trend, it's going to be the opposite. So ionization energy in terms of a period trend, as I move across the periodic table, as I move across a row, I need more ionization energy. So ionization energy will increase as I move from left to right. It doesn't take a lot of energy to remove that one little single electron. Doesn't take a lot of energy to remove that one little single electron from potassium, because it already wants to give it away. But as I move across, like for example, if I move to bromine, if I'm thinking about the same row, if I move to bromine, it has those valence electrons. It needs one more to be stable, to be full. So it doesn't want to give up any of its electrons at all. And because the nucleus is holding those electrons so tightly,